Suppose you have an angle, and you take the angle bisector, and you choose a random point on the angle bisector, and you draw perpendiculars from this random point to here and to here. Now you can immediately tell me that this triangle is congruent to this triangle because they have the same angles and they share a side, or you could tell me that the whole construction is symmetric with respect to this angle bisector. This is symmetric to this point symmetric to this point, and so on. In any case, we know the following properties. The length of the perpendicular equals the length of the other perpendicular, this length equals this length, and this angle equals this angle. Now we know that we can draw a circle that touches this line here and this line here and has center this point. Now suppose I take this triangle and I draw the three angle bisectors of that triangle. And my question is, do they intersect at one point here or do they not? What I'm going to do is I'm going to intersect two of them here, and I'm going to see if the third angle bisector passes through this point. Now I drop the three perpendiculars from this point to the three sides of the triangle. And now we have that this segment equals this segment, because this is a random point on the angle bisector of this angle, and we dropped two perpendiculars from this random point to the arms of the angle. And similarly, this is also a random point on this angle bisector, and therefore this perpendicular equals this perpendicular. Now I'm going to connect this point with this point, and I'm going to consider the two triangles, this triangle and this triangle. So they're both right-angled triangles, and they have one side here that is equal, and this side, which is common, so it's also equal. And we know that if we have two triangles that have two common sides and one common angle that points against the larger of the two sides, then the two triangles are congruent, and therefore this triangle is congruent to this triangle. But if it's congruent, this means that the angles here are equal. And so the green line is the angle bisector of this angle. But we defined the red line to be the angle bisector of this angle. And so the red line and the green line actually coincide. And therefore, the three angle bisectors in a triangle always intersect at one point. And this point is called the incenter of the triangle. Now notice that the circle with center, the incenter, and radius, this length, first of all passes through this point, and this point, and second of all is tangent to all these lines because of the perpendiculars we have here. And so this circle is called the incircle of the triangle, and its defining property is that it's tangent to all the three lines in the triangle. And of course, the center of the incircle, or the incenter, is always the intersection point of the three internal bisectors in the triangle. The natural question now is to ask, well, what about the external bisectors of the angles in a triangle? Well, let's take the external bisector of this angle, of the triangle. So we're going to take the complementary angle, and we're going to bisect it, and then do the same thing here for this angle, bisecting this angle here, and then we intersect them here. And it's our hypothesis that maybe the internal bisector of the third angle will pass through this intersection point. First of all, let's notice that the internal and the external bisectors always make a right angle. So this is a right angle here, and this is a right angle here. Now I took this point and I dropped three perpendiculars, one to each of the sides of the triangle. So this is the perpendicular to this side, this is the perpendicular to this side, so we needed to take the extension of the side so we can find the intersection point. And then the extension of this side, we drop perpendicular here. Now take a look at this angle here. There is an angle bisector, and a random point on the angle bisector, and then two perpendiculars are dropped like this and like this, and so they have equal length. For example, because of symmetry with respect to this angle bisector. This is symmetric to this, and so this point is symmetric to this point. Similarly, consider this angle. This is an angle bisector of this angle, and so this is a random point on the angle bisector, and we drop perpendiculars to the two arms of the angle. And so the lengths of these two perpendiculars are equal. Finally, I'm taking this green line to connect this point and this point. And now these triangles, this one and this one, are congruent because they have one angle here of 90 degrees. They have this side and this side equal, and this side in common. And the angle that they have, that is equal, points towards the larger side of the two that are common. And therefore, they are congruent triangles. This triangle is congruent to this. Now that we know that they're congruent, this green line is now the angle bisector of this angle. But we defined this point to be such that the red line here is the angle bisector. And therefore the red line and the green line coincide. This point, and this point lie on the same line, which is the angle bisector of this angle. And hence we can construct a circle with center this point and the radius this segment, such that it passes through this point, and this point. And it's also tangent to the sides of the triangle, this side of the triangle, this side, and this side. This here is called the excircle of the triangle. So this was the incircle, and this is the excircle. And we could have drawn the excircle with respect to this side, with respect to this side, and with respect to this side. So there are 3 excircles. For example, one of them would be here, like that, and another one above here. This point is called the excenter of the triangle. And so each triangle has 3 excenters, and this is one of them. And as you can see, the excenter is the intersection point of the external bisector here, and internal bisector here. Here is a picture of the incircle and the 3 excircles of a triangle. This is the triangle. So the 3 internal bisectors intersect at the center of the incircle, or the incenter. And then if we take the external bisectors, they're going to intersect at the centers of the excircles, or the excenters. So this is an excenter, this is an excenter, and somewhere in here is the third excenter. And so importantly, because this is the same external bisector as this one, we got a triangle here, a triangle such that the 3 initial vertices, this one, and this one, lie on the sides of this triangle, and such that this is a 90 degrees angle, this is a 90 degrees angle, and this is a 90 degrees angle. And that's because the angle between the internal and the external bisector is 90 degrees. Today we're going to have 2 optional problems. We have a triangle here, and this is the circumcircle of the triangle, and this is the circumcenter of the triangle, so the center of this circle. And we take 2 lines, this one and this one, such that they pass through these vertices, and we have that this angle equals this angle, and this angle equals this angle. And we take this point. And we need to prove that this point, and this point lie on a single line. So we need to prove that this here is a straight line. And here's the solution. The first thing to notice is that this equals this as a radius. And the second thing to notice is to consider this triangle, for which this is an external bisector and this is an external bisector. And so this is the intersection point of 2 of its external bisectors, which means that this, the line that connects this point and this point, is an internal bisector of the third angle, which is this angle. If we could prove that this here, with respect to this point, is an internal bisector of this angle, then it would follow that the 3 points lie on the same line, because then this line would be the same as this line. Now take a look at this triangle again and this point. This point lies on the perpendicular bisector of this side of the triangle, and we want to prove that it also lies on the angle bisector. And that must remind you of the fact that the angle bisector and the perpendicular bisector of the opposing side always intersect at a point on the circumcircle of the triangle. And so we only need to prove that this quadrilateral is cyclic, from which it would follow that this arc equals this arc, because they correspond to equal chords in the circle, and then it would follow that this angle equals this angle. Now let's call the angles of this triangle alpha, beta, and gamma. Then we know that alpha plus beta plus gamma is 180 because these are the angles in the triangle. We also know that this angle is alpha and this angle is beta. Now since this is 2 times alpha, the complementary angle here would be 180 minus 2 alpha. And since this is 2 times beta, this angle here would be 180 minus 2 times beta. But we know that the sum of the angles in this triangle is 180 degrees. So this is 180 minus 2 alpha and this is 180 minus 2 beta. So this angle must be 2 alpha plus 2 beta minus 180. And now we just need to do a little algebra with this expression. This angle is 2 alpha plus 2 beta minus 180, which is 2 times alpha plus beta minus 180. But alpha plus beta, because of this here, is 180 minus gamma. And when we expand these brackets, we get 180 minus 2 gamma. So this angle here is 180 minus 2 gamma. But now, because this point is the circumcenter of this triangle, and this angle is gamma, we know that this angle is twice as much, so this is 2 times gamma. And now we can see why this quadrilateral is cyclic. Because this is 180 minus 2 gamma, and this is 2 gamma, so their sum is 180 degrees. And now because it is cyclic, we know that this here is an angle bisector of this angle, And this here is also an angle bisector because this is the intersection point of the external angle bisectors for this triangle. And so the two angle bisectors coincide, and so these 3 points lie on a straight line. This is the second optional problem. We have a triangle and two of its internal bisectors intersecting here at the incenter of the triangle and intersecting the sides at this point and this point. Then we take this line to be symmetric to this line with respect to this angle bisector. And so this angle becomes equal to this angle. And we take this line to be symmetric to this side of the triangle with respect to this angle bisector. And so it turns out that this angle equals this angle. And we intersect these two here, and we need to prove that this line, defined by this point and this point, is perpendicular to this line. So we have to prove that this angle here is a right angle. And here is the solution. I'm going to continue these lines until they intersect the base of the triangle, and then I'm going to prove that this here is an isosceles triangle in which this is an angle bisector here, and therefore it must also be an altitude. First of all, let's note that this angle here equals this angle here. And so, because this angle equals this angle, we know that this angle equals this angle. Now consider this triangle here. We have an internal bisector of one of its angles, and it intersects the external bisector of the other angle, because this is an external bisector of this angle. And now, the internal bisector and the external bisector, we know that they intersect in the excircle of the triangle, in one of the 3 excircles. And therefore, this here must be an external bisector of this angle. Now, consider this triangle here. We have an external bisector here, and another external bisector here. So with respect to this triangle, these two are external bisectors, and they intersect at one of the 3 excircles of this triangle. And therefore, this here must be an internal bisector. Now take a look at this triangle, the red triangle. This is its incenter, because this is an internal bisector, and this is the other internal bisector, and they intersect here. And therefore, this here is an angle bisector of this angle. The last thing that we're left to prove is that this triangle is isosceles, and then it would follow that the angle bisector is also an altitude, and then we would get the 90 degrees here. Now let's call this angle here gamma. Then consider these two triangles, this triangle and this triangle. You can see they have the same angles because this angle equals this angle and this angle equals this angle, and therefore the third angle here, gamma, equals this angle here. And they're also, by the way, congruent because they share a side. Similarly, now consider this triangle and this triangle. They have equal angles because this angle equals this angle, and this angle, the large one, equals this angle, the large one also, because these small angles are equal, and these angles here are equal. And so the third angle here is gamma equals this third angle here, gamma. And the triangles are also congruent because they share a side. And therefore, in this triangle now, we have that this angle is gamma and this angle is gamma, and therefore the triangle is isosceles as desired.